to be looking at exponential functions. So we're going to evaluate exponential functions, identify whether a table represents an exponential function or not, and then we're going to graph exponential functions. So here we have a table and graph that show the insect population increases over time. So there's two things that we will see with exponential functions. Normally, that either they are growing, like this insect population is doing. So as the graph moves from left to right, it's going to be getting bigger and bigger. And so it's increasing at what we call an increasing rate. So the jump between each number is always getting bigger and bigger. Okay? Or if it's decreasing at a decreasing rate, which means then that the graph is going down, well then the gap between each number gets less and less each time. Right? So we have those two things that happen. Right? So first of all, we're just going to look at what an exponential function is. So when we do have an exponential function, we have, like to have here for this situation, it's f of x equals 2 times 3 to the power of x. And which is the general form, which they have written here, is f of x equals a times b to the power of x. So for an exponential function, we will always see it in this form. A times b to the power of x. Where a is what we call our starting value, and also it's the y-intercept. So this is starting value. So if we're talking about a word problem, then that value is always going to be the initial population or the initial amount that we start with. So it's the starting value, and that's also, when we graph it, that's also going to be the y-intercept. And b, we call that it's either our growth rate or decay rate. All right? Tells us if it's increasing, then it's going to be growing, and if it's getting smaller, then it's going to be decaying. Right? All right, so in this problem with the insect population, it started with 2, so that would be my value of A, and then each time they multiplied by 3 to get to the next number, and so that's our growth rate. It's tripling each time. All right, so that would be the value of B. All right, so first we're just going to do a couple problems where all we are doing is using our calculator just to evaluate a couple of functions. So here we have f of x equals 500 times 1.035 to the power of x. This amount is the amount of money in a certificate of deposit after x years. How much money will there be in 6 years? And so all we're going to do is we're just basically putting that in our calculator. So we want to find after 6 years, so we're trying to find f of 6. And that just means that we're replacing x with 6. Okay, so we get $614.63. All right, so after 6 years, the certificate is worth about $614.63. Right. All right, so find this one. All right, so with this one, once we plug in 7 for x, we get approximately 173,625. So definitely when I write this answer, I'm definitely going to round to the nearest whole number, right? Because we're talking about people or objects, and so when you have those situations, then you're going to round to a whole number. So in 7 years, the population of the city would be approximately 173,625. Now, two things to notice about these two problems. One is in letter A, the number got bigger, and letter B, the number got smaller. So what thing made it go up in A and down in B? Sorry?
B, the value for B is less than 1.
Good. Okay. So from f of x equals a times b to the power of x. So in our exponential functions, if b is greater than 1, we have growth. All right, so it's going to get bigger. It goes up. And if b is actually between 0 and 1, okay, then we have decay, so it goes down. Now that works when we're talking about an application problem. If we're talking about graphing, then it kind of depends on what A is to reflect that also. So A can cause it to change a little bit only just because if A is negative. That's the only way A would affect it. Right. So B is greater than 1, we have growth. B is between 0 and 1, we have decay. All right, good. All right, so how do I know if a set of data represents an exponential function? All right. And so what we do is we'll do just like we did yesterday. We will divide. We'll try to find the common ratio and see if it is the value we need it to be if they're all the same. Right? So remember, linear functions have constant first differences, quadratic constant second differences, and exponential functions, they don't have constant differences but have constant ratios. So as the x values increase by a constant amount, so we always have to have our x values always must go up by the same amount, whether it's 1 or 2 or 3, doesn't matter, as long as it's always the same amount. Then we're looking for our ratios. So if we did 162 divided by 54, then that would equal 54 divided by 18, which equals 18 divided by 6. So these ratios are all going to have to be the same. So when I think about them, I always start with the one in the last one and work my way backwards. Right? Makes it easier that way because you're always supposed to do the next one divided by the previous one. So here we have two examples, and we want to see if they represent an exponential functions. So the first thing you need to do is check your x's. Make sure the x's are all changing at a constant rate. Right. Then check our y values to see if they have a common ratio. All right. So we have to make sure that the ratios are all the same. So we've got 0, 4, 112, 236, 3, 108. A lot of times you can look at them and say, yep, I can see it, they definitely are. Okay. Other times we definitely can't. So, Michael, what's happening with these y values here? Okay, they're multiplying by 3. All right. So if you can see that, then it makes it easy and say, okay, that is an exponential function. So 0, 1, 2, and 3, those are all going up by 1. And then if I take my y values and I divide them we can see that they all change by our common ratio of 3. So our value of r in that situation, or value of b, would be 3 here. Right? So this represents an exponential function. And yesterday when we talked about the value of r, that actually is the same as the value of b. So in this case, r is equal to 4 or to 3, or we could say that b was equal to 3. Those would be the same thing. So if I was going to write the exponential function here that's represented, then we would say that f of x equals, our starting value is 4 times 3 to the power of x. Right? So when x is 0, y is 4. So that's always your starting value is going to be your y-intercept. Right? So that means the x value would have to be 0, so the y value is 4. Okay? All right, letter B. We look at these. Do they all change by 1? Yes, going -1 to 0 to 1 to 2. These are all still going up by 1. Then we want to check our ratios. So 125 divided by 64, is that the same as 64 divided by 0? Is that the same as 0 divided by -64? Are those all the same? Well, first of all, you can't divide by 0, right? So that is impossible. Second of all, 0 divided by 64 is 0. Okay, so these are not the same, so this is not an exponential function. And here, key to you is this: if you ever have a y value of 0, it cannot be an exponential function. All right? With exponential functions, y can never be 0. As far as a true exponential function is concerned. Now, when we get into looking at transformations and stuff, then things can happen there. But right now, if you have 0 as a y value, it's not exponential. You can look at it right away and say, boom, it's not. I can tell that because y can't be 0. Because everything's got to be in the form a times b to the power of x, and there's no way when I take a can't be 0, right? A can never be 0 because what happens when I multiply by 0? I just keep getting 0. Okay, so a can't be 0, and so there's no way to get 0 when I multiply by another number other than 0. Right? So if we go back up here and look at this, or over here, right, it says a can't be 0. B can't be 1. Right? So do these two represent exponential functions or no? So we're just checking to see if the y values, when I divide them in order from the last one to the first one, right, do they give you the same value? If they do, it's exponential. And that's our common ratio r, or we could call it b, because in this case, in this situation here, this would be, our function would be f of x equals, the initial value we're talking about is always the y-intercept, so the point 0, 1, so this would be 1 times, our value of r is 1/2, so 1/2 to the power of x. So that is the function that we're working with there. Just if we go backwards, then it gets bigger, because here, since r is 1/2, the numbers are getting smaller each time as we keep going. Okay. All right, so we looked at just evaluating exponentials, telling to see whether an exponential function or a set of data represents an exponential function. Now we're going to do some graphing. Okay. To graph an exponential function, choose several values of x, positive, negative, and 0, and generate ordered pairs. plot the points and connect them with a smooth curve. All right. Now, so we're going to look at a couple different possibilities here. The first one says graphing y equals a times b dx, with a greater than 0 and b greater than 1. All right. So we're talking about a graph that's going to go up. Now, there's a couple different ways you can do this. All right. And I would look at it, I want you to do it the simplest way. All right. So let's start with our values of b first of all. All right. Well, actually, we're going to start with the y-intercept. So the y-intercept, when x is 0, y is going to be 0.5. All right. This is always our y-intercept. All right. All right. The value of a is our y-intercept. So we can start there. Now, the thing is next is to think about what does that mixed number tell us? What does the value of b tell us? And what the value of b tells us, b says we multiply by that number. All right? So we're just going to multiply by the value of b. So when I put a 1 here, and I take 0.5 and I multiply it by 2, what do I get? 1. Right? And then I put a 2 here. So I'm going to multiply by 2 again. Right? So we're multiplying by 2 to get there. So we multiply by 2 to get the next number. Right? So what's 1 times 2? 2. All right? All right, we multiply by 2 again. 2 times 2 is 4. Right? And so then we can just plot those points and draw our graph. So think about it this way. The value of a, that first number is our y-intercept. So when x is 0, that's my y value. And then whatever b is, we're just multiplying by that to get the next number. Okay? So when I go to graph this, we have the point 0, 0.5, 1, 1, 2, 2, and 3, 4. All right, so this graph it's a nice smooth curve then that we draw, so it looks like this. And make sure you have arrows on both ends, and this graph does not cross the x-axis. Okay, all the graphs we're going to draw today, they never cross the x-axis, so make sure that you don't do that. So we'll start with the y-intercept, and then just multiply whatever the value of b is each time. Plot a few points, draw a graph, and the thing to remember is, so whenever b is greater than 1, a is greater than 0, it's always going to be exponential growth, so the graph is going up. All right, now we're not going to do this one because this one is basically the same graph. Just, what's the y-intercept for this one? Okay, yes, it's 1. All right, the y-intercept is 1. If there's no value of a, then the value of a is just 1. All right, so when a is greater than 0, b is greater than 1, we have exponential growth that will look like this. Okay. All right, a is less than 0 now, and b is greater than 1. So we still have an exponential growth situation, except since a is negative, all of our values are going to end up being negative. All right. So it's going to look a little bit like that one we just did, except it's going to be a reflection, right, over the x-axis, because instead of all my values being positive, they're all going to be negative. All right, so let's start with our y-intercept again. Our y-intercept is negative 1/4. All right, we'll do 1, 2, 3, and 4. Now, I know they said to do negative values, but you can see what the graph looks like, and so it just keeps going with that pattern. So, I mean, we could do some, and we'll look at it on your calculator in just a minute on this one. All right, so the value of b once again is 2, so that means all we're doing is doubling the values all the time. We're multiplying them by 2. All right, so if I take 1/4 and I double it, what do I get? Okay, negative 1/2. All right, 1/4 times 2 is 1/2. All right, and it's negative because I'm multiplying it by a negative number. All right, so then I multiply that by 2. All right, 1/2 times 2 is 1, so we have negative 1 here. And then we multiply that by 2, negative 2, and multiply that by 2, negative 4. So then we plot those numbers on our graph. I can't do 1/4, but I can do. All right, so we can see the pattern that's here. That with the pattern, all right, keeps getting closer and closer to the x-axis, but it still never touches it. All right, and so this graph looks like the one we just did, except for it's a reflection over the x-axis, right? Because all the values are positives or negative instead of positive in this situation. So that would be that's the easiest way to graph these, right? Graph your y-intercept, find the y-intercept first, okay? And then whatever b is, we multiply it by that number. Okay? So if we put this in our calculator, okay? So we've got, let's see, negative 1/4 and times 2 to the x. Right. We can see here, now it looks like the graph crosses the x-axis, but actually just keeps getting closer and closer to it. So if we looked at our table, oh, hey, we can see that as I go up, these decimal numbers keep getting smaller and smaller, closer and closer to 0, but they never actually become 0. I mean, if you went far enough, it might say 0, but they never actually go there. Right? So you could use your table on your calculator to find the points and plot them also, but it's pretty easy just to do a little bit of simple multiplication. Okay, let's look at the next one. All right, now we have b is between 0 and 1. So we're talking about decay situation. b is between 0 and 1. Now let's go ahead and put this one in our y equals, first of all, just to see what the graph is going to look like before we do it up here, because you actually need some negative numbers in this case to give you some better values. So negative 1 times 1/4 to the power of x. So here's what a graph looks like. So in this case, all right, so we can see the graph. Let's go ahead and work on what we were just doing, how we were doing these, all right? So I was putting in my y-intercept first, all right? So at 0, we get -1. So now we're multiplying by 1/4 each time. So what's going to happen to all my numbers now? They're going to keep getting smaller and smaller, in other words, getting closer and closer to 0. Because now I'm going to get -1/4 when I multiply by 1/4 the first time. All right? And multiply by 1/4 again, well, now I'm at -1/16. Well, that's getting small enough it's going to be hard to plot that graph. So we need to go the other way a little bit too. All right? So it'd be good in this situation to actually do some negatives. Well, when we're doing it with the negatives, then we have to think about it going the other direction. So if I had -1/16, -1/4, -1, what would it be then if I put in -1 for x? So remember, since we're multiplying by 1/4, if we're going the other direction, then we are going to divide by 1/4, which is the same as multiplying by 4. So this would actually be -4. So if I multiply each time as I'm going down, because it says b is 1/4, if I go up, then I'm divided by 1/4. And the same as if you look at the other ones here, all right? So if I'm multiplying by 2 to get from one to the next to the next, if I go backwards, I'm dividing by 2 to get there. Just doing the opposite thing. And so sometimes when the value of b is a fraction, okay, sometimes it gets real small real fast, and so you have to have a couple negative numbers or at least one negative number to help you to see the graph. Right? So we've got -1, -4, 0, -1, and then my other ones are real close here. All right. So two things to remember. One, make sure you got arrows. Two, as you're getting closer to the x-axis, make sure you don't curl it back this way. All right? Because that doesn't happen. It just keeps getting closer and closer to the x-axis, but doesn't actually touch it. All right? So be careful with your graphs there. All right? And if this is when a is negative, if a is positive, then it's going to look the same, but it's going to be up here. All right? So when a is positive and b is between 0 and 1, the graph is actually going to be above the x-axis. But as it goes to the right, it's going to get closer and closer to 0. All right, last thing. Here's an application problem. 2000, each person in India consumed an average of 13 kilograms of sugar. Sugar consumption in India is projected to increase by 3.6% per year. At this growth rate, the function 13 times 1.036 to the power of x gives the average yearly amount of sugar in kilograms consumed per person x years after 2000. Using this model, in about what year will sugar consumption average about 18 kilograms per person? Right. So we've got this function. This tells us how much sugar is being consumed by people in India, and which means it's growing 3.6% per year. All right, so since this number is large, our value of b is larger than 1, it's growing. And so we want to know, when does it hit 18? All right, so we've got a couple different options. We can just start with, put it in our calculator. All right, we graph it. I'm really not going to use our graph. We're going to use the table right at the moment. But all right, so I can't see much of that graph, can I? Okay. So the thing you have to remember is that our y-intercept is 13, and it's getting bigger from there. So my window I have when I hit zoom 6, the standard view window is this only goes up to 10. So I need to have my y values, my y max needs to be a lot higher so that I can see it. Since the y-intercept is 13, I know it's going to be at least 13 to start with, and it's going to get bigger. So let's go to 25. And we only need to see as far as 18, but we'll do that. Well, it looks like, all right. So it looks like I might need to go farther down just to be able to see 18 because we're going by 5s here. So 5, 10, 15, 20. So I'm going to change my x's also. Let's go to 20. X max. Just so I get a little better view of the graph. There we go. All right. Okay, so we go to our table then. See if we can find 18. And 18 looks like between 9 and 10 on mine. Okay. So we would say in about 10 years, the sugar consumption in India will be about 18 kilograms. Now, can we find the exact value though? All right, we can. So here's what we want to do is we're trying to solve this equation. That when does this equal 18? Is what we're actually trying to solve. So what I'll do is I'll go and put in y2 on my calculator. I'll put 18 in there. Now when I graph it, I can see that these two lines intersect. And I know it's going to be between, what was it, 7 or 8, 8 or 9? Okay. All right, so then if I do second trace, I can find the intersection point. So second trace is number 5. And then our first curve is our equation. Second curve is the 18. And our guess. Okay. So it tells us it's 9.2 is approximately the exact value, but we're always going to want to go past that when we write an answer. So we're going to say for our answer that x is approximately 9.2 years. And so when I write my sentence here, then I can say, it says years after 2000. Right? So let's see. The people in India will consume 18 kilograms of sugar between 2009 and 2010. Right. I should say we'll consume an average of 18 kilograms of sugar between 2009 and 2010. Right. So make sure, because it says years after 2000, that we include that into it. Right. So you can't just say in between 9 and 10 years, you have to say between 2009 and 2010. Okay. All right, so we've got just evaluating exponential functions, checking to see whether a set of data represents a function, drawing some graphs, right? And then solving the problem. So when you get to solving these problems, then just put your value you're trying to get in y2 and find where they intersect.